Hello. We've covered how neural networks, convolution neural networks work. Essentially, they have a detector portion and then they have a classifier part, right? So you have for a given input image, if you know what the label is, you pass that input image through the convolution neural network, which essentially applies a bunch of correlation filters on them, produces feature maps, which are then pooled and flattened and fed into the classifier part, which produces a prediction label. You compare that prediction label to your target to compute a loss, which then is used to update your classifier, your weights in this bit, and as well as your filters. And you can have one or more than one filters. You can have a whole bunch of filters in the convolution neural network. You can actually have even multiple layers of this detector portion. You can have multiple convolution blocks, and you can have the output of those convolution blocks feed into your classifier, and you can have a pretty deep network for your classifier as well, or the fully connected portion of it. And then you can use this whole thing can be trained as what is called end to end, and the only thing that we need is the output label, which is then compared to the given target. We don't need these detection outputs in the middle, although this would produce some interesting detections or these feature maps, which can be really used for visualization of what the neural network is working or learning, right? What we are gonna do is we're gonna try to understand why these convolution neural networks are a good idea. And one thing that we have discussed earlier when we were talking about fully connected neural networks was that the input dimensionality, if you feed it in the whole of the input image, that's going to be really large. What these neural networks, these convolution neural networks allow us to do is to reduce that number or that complexity by a significant amount using something called local weight connectivity and shared weights. Sounds really complicated, but since we have already understood how convolution works and how these convolution neural networks are programmed and how they produce their output, we this should be really easy for us once we get to once I define these terms. Similarly, these convolution neural networks learn what are called hierarchical representations because you have, if they have multiple layers, then the first layer can learn low level primitives. The next layer is going to is or is expected to learn higher level primitives of the given classification problem, and we're going to see how. Okay, so let's first talk about what happens in convolution. You're given an input image which is convolved with a filter, right? So if this is your filter over here, this is your input image, then all that happens, or the dot product, is localized within this region when this convolution is taking place at this point within the image. We can then go ahead and stride the neural network, the filter to the next position. But at a given position, the only thing that is being multiplied is this bit of the image that is highlighted in red with this filter. So there's, if you represent each of this image, so if you represent the convolution output of this filter with this input image, what you're gonna see is an image like this, which in this case is a 4 by 4 image. That is the output of all the convolution, right? But if you focus your attention onto a single run or a single dot product within this convolution block, then all these weights are being multiplied with these weights over here within this red square. So if you flatten this output of the whole input image, the input image is going to be 36 dimensional because there are 6 by 6 pixels in here. But when you do the dot product within convolution, the only thing that is producing this 3 is simply the first 16, sorry, the first, so for this particular pixel, for example, the only thing that is getting multiplied is this one is getting multiplied with this minus one is getting multiplied with this one is getting multiplied with this one, and so on, right? So it's very localized. And once we move it to the next pixel, we can have another representation, but for a given point, we don't have all weights feeding into or all inputs feeding into the same neuron as would have been the case if you had used a fully connected neural network. So that's the first thing that we notice. So because the input is only connected to only 9 inputs, it's not fully connected, therefore we get less number of parameters, right? So that's a good thing. The next bit is even if we move this input, so once we have this input filter, we once we stride it forward by one pixel in this direction, It's the same filter that is being multiplied. We don't have another filter that is being multiplied with this one. It's the same filter, or every filter in the convolution neural network is going to be multiplied first with this part that I showed as the thin red block, and then the same thing is going to move into the next block. So then since it's the same filter, we're not creating more parameters. We end up with this thing, that the weights are being shared across different regions within the input. And what that leads to is that it has even lesser number of parameters. So we don't have that parameter explosion that we would have expected in a fully connected neural network. The third bit, and that's also a good thing. So this, we have a shared feature representation. We have localized weights because that is the way convolution works. So that is, from a computational perspective, that is how these neural networks are able to learn more efficient representations, especially for images. Another good thing, or if you think about it in a bit more detail, or if you have worked with images, then most of the pixels in an input image are actually correlated. So a pixel over here is no different from, typically not much different from the pixel next to it. And these neural networks, because they are localized and because they share weights, they're able to learn these sort of correlations within the input image. And also because convolution is invariant to translation. So if you or equivariant to translation, we have, if you have got an input image with an object at a certain position, you convolve that with a given filter, you get a certain output. If you move that object in the input image, the output is also going to move in a corresponding amount. So it reflects a fundamental property of object detection. So if you want to detect an object in an image, it doesn't matter where it is, right? So that's what these shared weight and localized representation allows us to learn in a convolution neural network. The third thing is that's interesting about convolution neural networks is that they represent a sort of a hierarchy of features. So let's say if we want to detect a bus, one way we can do that directly is to convert these pixels, and then we can pass those pixels to the original input image, or to a classifier, and then that can generate a label of whether it is a bus or not. However, the number of pixels in the input image is pretty large, therefore we can have a very large input dimensionality for this classifier, and that is going to really create difficulties. We can also extract features from the given input image that can be representative of what object is in the given input image. Let's say we can extract some edges, we can pass those to a classifier manually. We can extract these edges or these features, and then we can use a classifier for object detection, right? And in the same manner, we can have these what are called more sophisticated or computer vision guided features like SIFT or histogram of oriented gradients, and all those type of features in which we can extract edges and see how they are oriented in terms of histograms. And then we can pass that into a classifier. We can do some k-means clustering on top of that, and so that a certain collection of edges is what is called a bus, right? If we have this a specific pattern of edges, if we had two parallel edges over here, we have got these two edges, and we extract those edges manually, we pass those to a classifier, we should be able to learn better. So this is how you would do manual representation learning, or feature extraction as it is called. You can have very shallow level features in which you have raw pixels, or you can extract more deeper features in the sense that these are more representative of what the object actually looks like, and you can use those to your classifier. The problem of learning becomes easier the better features you have, right? So you can have a smaller classifier if you have very good features as the input that allows to work equally well. However, what these neural networks allow us to do is do all of this process from this shallow to deeper learning in a completely automated manner. If you've got enough data, we should be able to learn, each of these layers should be able to act as a detector of these important features, so you can get essentially what is called a hierarchical representation learning for object classification and detection tasks. So for example, if your object is a car, you can have these low level features which are essentially edges. So filters, the original filters in the input image can learn very simple features like edges, which can lead up, because we are then trying to learn on top of these, we have convolution layers on top of these features, we can learn more complex features like circles and tires and so on. And then we can move even into a higher level features that allow us to learn these more complex features. So, for example, what a fender looks like or what the windshield looks like, and then we can pass these on to a classifier that allows us to classify these. So the feature visualization of convolution neural network can be a very powerful tool in order to understand how these neural networks work. And there's a very good demo of that that I provided as a link over here that we're going to discuss next. So this particular demo is this is an excellent demo. First of all, it tries to solve the CFAR10 classification problem. So it's essentially an image classification problem in which you have 10 different types of objects in the input, and what it shows is it trains a neural network within your browser and allows you to visualize different feature maps of different layers at within your neural network. So it builds a convolution neural network, and then we can simply, so it doesn't require you to program anything. You can just specify different type of parameters over here and watch how your neural network learns. So this is the structure of the neural network. You can have it has multiple convolution blocks, as we are calling them. The first convolution block has 16 filters in it with a stride of 1 and a padding of 2, and we have an activation of the rectified linear activation over here. And then you have a pooling block which performs pooling with a stride of 2. I think it's maximum max pooling over here. And then you can have the output of that is passed on to the next filter, which is next block, which has 20 filters, convolution filters in it. And then it has a third block which also has the third convolution block which also has 20 different filters in it. The output of this is then passed on to a classifier which produces 10 different labels, and that's basically the structure of the neural network. And if you have an input representation, for example, this image that contains a boat, we want to classify that this object contains a boat. You can have another boat over here. This is a different type of boat, and you have passed that as an input image, and then you want to classify whether there's a boat in there. There are different types of objects. But what the power of this demo is that it allows you to visualize as the neural network is training. So you can have neural network training over here. You can see or you can watch how these losses go down in your neural network, and what are the activation feature maps of at the output of each of those convolutions. What do they look like? So if you have a cat as an input, you can see that there are filters that localize the cat, right? So there are activations that have a high value for the cat at the final convolution block. If you go a bit lower, you can also see different type of activations within at different layers, and you can observe the output of each of those pooling and convolution blocks within your input image. So you can see that if you go into the very initial layers of your neural network, you are simply observing, you are extracting some features over here that produce or generate images where there are edges, and then those are fed into the next layer after pooling, and then those produce essentially a positive pixel at a particular location, ideally where that particular object is, and then those are pooled, and then those are passed on to the next layer, and then you have essentially an activation that takes care or generates a prediction label. So just to recap, for a given input image, this is the output that we generate. We have 10 different objects, so a high value at a certain object indicates that type of the object, and we compare that to that input image or a given input image. We know that label. We try to compute the loss and then feed that back as input. So for example, currently for this particular input image, the neural network thinks that it has a high probability of being a horse, which is wrong, right? So it compares that to the target label, and it tries to minimize that classification error by optimizing over the filters that it's trying to learn. And filters and the classification, the classifier weights. So you can observe the activation of each of those neural networks, the convolution blocks, as well as your activations. So ideally, we should have, so for example, if this were a deer, we should have this has a high probability. This currently the neural network thinks that this has a high probability of being an aeroplane, and you can watch this neural network train But the interesting thing that you really need to look at is how do these activations change within the neural network representation as the neural network is training. Since it's going to take a long time for this neural network to converge, perhaps it would be best if we skip this bit and move to, we can simply load a pre-trained neural network, and then we can visualize its output of what it's learning at different layers. And I welcome you to play with this demo and try to understand. The goal of understanding this, or the goal that I would like you to have, is how do signals, supervisory signals only available at the output layer of what the object type is, are fed back, and how are those convolution filters being trained within at each layer of the neural network, and how do those fit into the hierarchical representation learning thing that we discussed. Thank you.